We have already talked about the definition of ideal, but I would like to repeat it. An additive subgroup N of a ring R satisfying the properties A times N subset of N and N times B subset of N for all A and B belonging to R is an ideal. So let us see one example, one known example with us. So I would like to go to Z6. What are the elements of Z6? And let me take its a subset. I mean a subgroup N at 0, 3. Is it really additive subgroup? Tell me. Does this form additive subgroup? So if I start with 0, 3 along with addition, let me have 0 and 3. Yes, come up. So what are the outputs you are getting? 0 plus 0 is 0. 0 plus 3 is 3. Again here 3 and 3 plus 3 is
1.
no.
0.
Sorry,
ma'am.
How 0? It is going modulo 6. So 6 divided by 6 remainder is 0. So what you observe, it is binary. Addition is binary in this set. So N forms additive subgroup of Z6. I suppose you are following. Now the question comes of ideal, definition of ideal. What they are saying, you take all A, B belonging to R, multiply by A to the left side, still whatever you are getting is subset of N, multiply on right, still you will get a subset of N. So what I'll do is I'll multiply elements of N by all those elements. So suppose I first multiply because 0 into anything goes to 0, so I won't deal with it. 1 into the number remains the number as it is. So I'll not deal with 1. Let me go with 2. So 2n. What will happen? Come on. 2n. Twice 0, 0. Twice 3. I'm multiplying elements of n.
0.
Yes, it still is 0. So I got a singleton 0 set. If I ask you about 3n, what is going to happen? Just help me. 3 zeros are 0, damn sure. 3 threes are
3.
3 threes is 9 divided by 6. It gives us 3. Very good. So 3n is 0, 3. Means n itself. So I can say it is a subset of n. Can I? Here also I got a subset of n. Now let me start with 4. 4 zeros are
0. 2.
0 and 4 threes are come on.
0.
Still 0.
0.
So it is singleton 0, so it is subset of n. And now what is left is simply 5. So what is 5n? What is 5n? 5 zeros
0,
are
3.
0. And 5 threes are 15 divided by 6. Remainder is 3. So I'm getting the same set back. So in each case, what you observe, if I multiply on the left, I'm getting subset of n back. Followed me? Do you agree? So if I multiply by any element of Z6 on the left, I'm getting a subset of n. And if I multiply on the right, then what will happen? Yes. So you can see in Z6 multiplication is commutative. And it being commutative, what you'll get is twice n will be the same as n into 2. N into 2 will also be the same set as twice n. You can check whether you multiply on left or on right. You are getting the same answer here because multiplication is commutative. Followed me?
Yes, ma'am.
Yeah. So this n is actually an ideal in Z6. So I hope you'll just note it down in your notebook or just take a screenshot of this particular screen. Ready for the next?
Hello, ma'am.
Huh?
Ma'am, whenever we consider as a commutative ring, then what we have to consider?
No,
Either
actually,
it is
yeah,
commutative with
yeah.
addition.
If it is not a commutative ring, then what you'll do is, see, basically, your question I now understood. See, we are talking about additive subgroup. So basically, I have to check whether my n is an additive subgroup or not. Have to check it. So very basic thing, it must be a subset of my original set, original ring. Second thing, addition must be binary in it. If so, then automatically it becomes additive subgroup. Is it fine? It must be very basically, first of all, additive subgroup. That is the first needed thing. What next? Next, we are checking by each and every element of my parent set. What is my parent set here? Z6. So we try with every element. If I multiply on left to the set, multiplying to the set means multiplying each and every element in that set. So if that set becomes a subset of my original n, in that case, I try with the next element and next and next. I just go on continuing, and once I confirm that every of these kind of sets are subsets of n, then I try with right side also, right multiplication also. If the multiplication is not commutative, then I'll have to go by both ways, left also and right also. In both the cases, if these two are satisfied, then I say n is an ideal. Followed? Got my point? Okay.
Means if it is not commutative, we have to check in both the cases.
Yeah. If multiplication is not commutative, then you multiply on left also, then go for right also. That is why the definition constitutes of both sides. Left multiplication also and right multiplication also. Okay.
And if it is not same, then it is not ideal, no?
Actually, if it is not contained in n, then it is not an ideal.
Okay. Means it,
Yeah.
just like subgroup in group.
Yeah. So let us go with one more example here. The non-example, let us deal with. See, f is the set of all functions from R to R. This I mentioned last time, but we were in a hurry. So let me once again focus on it. So I have the set of functions. F is the set of functions from R to R. Now, what kind of functions are they? Simply it is mentioned that they are real valued and their domain is also real. So all such functions we are taking under F. Now, let me take only constant functions in C. What C contains? C contains all F. From where I'm taking those F? From capital F. And how are they? They are such that F of X is constant. Let us say the constant is K for the time being. So obviously, I'm taking elements from capital F, means this has to be subset of capital F. Okay. Now, what they're asking you, C, whether C is an ideal or not. Whether C is an ideal or not. So I have to check it. So you select any function. You select any function from this capital F and multiply by that function to the C. So we are choosing sin x, and by sin x, let us multiply to this whole of c. What is going to happen? If I multiply by sin x to complete c, I'll be getting set like there was a constant, means maybe it is half somewhere. So I got half sin x. Maybe my constant is a pi. So I may have pi sin x and so on. So are these constant? Are those functions constant? Is half sin x a constant function? What I mean by constant function, if I input some x, value will not change, value will remain the same.
It is
So if I
not
input
constant.
x equal to 30 degrees, what is going to happen with half sin x? It will be 1 by 4.
1 by
If I input x as 90, value will go to
1 by 2.
into 1 means half. If I input x as 2 pi, what is going to happen?
0.
0. So values are differing. They are not constant. Means sin x multiplied by c cannot be subset of c itself. C contains only constant functions. Only those functions whose output is constant. So half sin x is not going to produce you constant output. Neither pi sin x will provide you. So it is not possible at all. Why to deal only with sin x? You may go with x into c. If you go with x into c, what is going to happen? This will be half x, or I can say x by 2. So this value also changes according to x. So this is not a constant function. So I cannot say it is subset of c. This basic thing, I hope where I'm pointing out, a times n is not a subset of n in this case. Any function multiplied to the set c is not a subset of c. And that is why c cannot be ideal of f. C is not an ideal. Followed? All right. So suppose somewhere you are getting my point. Now let us move ahead. Let us move ahead here. They are taking the same f as above, and n they are taking as subring of all functions f, such that f of 2 vanishes. What kind of functions they are selecting? At 2, the value of that function becomes 0. So is this n an ideal? That is a question. So what you want to check? If you multiply by any function to n, will it be a subset of n? So you can check here. You have any function f with you. Let us take another function. Let me call it a g for the timing. Let me take g. And if I multiply by g to the whole set n, will it be a subset of n? This is your question. Will it be a subset of n? G times n, will it be a subset of n? So n contains functions. And what kind of functions you are collecting? All functions f whose image is 0 at 2. So suppose the set n contains some f. If I say f belongs to n, then what will happen? Gn will talk about gf. Now if I am talking about gf, I have to check whether it is a member of n or not. Have to check it. The condition is at 2. The value comes out to be 0. So I have to discuss what happens at 2. So this is going to be g of 2 into f of 2. I don't know what happens to g of 2, but I know certain that f of 2 is 0. Why? Because f is chosen from n. So this is going to be g of 2 multiplied by 0. Followed my point? And the answer goes to 0. Means what you reach to? G into F at 2 is 0. Means GF belongs to N. GF belongs to N. Let us once again peep back and see what G and what F we are considering. So F is a member of N and G is any random function I have chosen from F. So any function G multiplied to set N, we are checking what happens. So if I multiply by G to N, means I'm multiplying every function in N by G. And to check whether the thing goes back in N or not, I just count it. So I calculated the value of GF at 2. So it becomes G of 2 into F of 2. I repeat, it becomes G of 2 into F of 2. And F of 2, you know better, the value is 0. So what you got? You got the answer as 0. So GF belongs to N. Followed my point? Okay. Okay. So GF belongs to N, but this F is just a representative function. It's a member of N. It is not a fixed one. It is just a token we have taken. So what this means, Gn completely is inside N. So Gn is a subset of N. Same way you may try with N into G also. And because the value goes to 0, there also you'll find that N into G is also a subset. N into G is also a subset of N. So both ways your condition is satisfied. Gn is also a subset of N, and G is also a subset of N. So this N becomes an ideal. What was your N? The set N was subring of all functions whose image at 2 is 0. So N is an ideal. Followed? Okay. Okay. Now I would like to proceed ahead. And we want to discuss about the factor ring now. Or the same we call as quotient ring. Either we will label it as factor ring or we will call it as quotient ring. So how is it defined? You have ring R. Let N be an ideal of ring R. Then the additive cosets of N form the ring R by N. Now you know better what are cosets. So cosets are of the type A plus N or B plus N likewise. What are A and B? They are members of R. How to define addition on the set of cosets? So you take two cosets with you. You can see this is your first coset, this is your second coset. How you are adding them? So it is just coset due to A plus B. And have to multiply them same way A into B plus N. So this kind of operations, they help this N. So R by N becomes a factor ring along with these two operations. Followed the definition. Should I repeat?
Yes.
Okay, I would like to repeat it. R is a ring, okay. N is ideal of R, okay. You take all kinds of cosets of N. What are meant by cosets of N? What are cosets of N? You can check here. This we have already dealt with. If you are saying your ring is R, I would like to go with one example. Just now you have seen Z6 and you have seen the set 03. So what I'll do is, I'll just go with different kinds of sets formed out of this. What is Z6? So let us go here. Its first entry is 0. And if I add this 0 to this n, what is n? Let us label this set as n. What is going to happen? 0 plus a number remains the number itself. So I'm getting n back. Followed me? So my first member here is 0 plus n. Then I continue with my second element, that is 1 plus n. What this 1 plus n going to produce?
1, 4.
1 comma 4. Okay. Then I move next. I go with 2. 2 plus n. What it is going to give me? 2
2,
plus 0.
5.
Yes, very good. 2, 5. All the elements of Z6, are they covered? Yes, I think so. 0, 1, 2, 3, 4, 5. All the elements of Z6 are covered. So I can stop here itself. These are the only 3. But let me check. Let me start with the next element, 3. And I add 3 plus n. What is going to happen? Yes, come up. 3 plus 0 is 3. And 3 plus 3 is 0. I'm getting the same set as this one. If I go with 4 plus n, what I'll be getting? 4 plus 0,
4, 1.
4 and 5. So I think you have got the concept. Is it right? So only 3 different cosets I got. So let me list them. 0 plus n, 1 plus n, and 2 plus n. Okay. So the set of cosets now I'll be labeling as what? Factor ring. Followed the concept? This set forms factor ring, or I can call it as quotient ring. But whenever we are saying it's a ring, then I have to go with some operations. First operation is of addition. The second operation is of multiplication. So you have to go with this operations. How would you go? How would you go? So we have to tabulate them. We are talking about addition. Let us tabulate 0 plus n, 1 plus n, and 2 plus n. Vertically also I'm having the same sets. And horizontally 0 plus n. I'll have 1 plus n here and 2 plus n. So I hope you will help me in addition. What will be the addition of 0 plus n and 0 plus n? You can see 0 plus n set is in front of you. Respective elements you're adding. 0 added to 0. I'll get a 0. 0 plus 3. I'll get a 3. 3 plus 3. I get a 0. So I'm just in the same set. So the addition is 0 plus n only. So if I add 0 plus n to 1 plus n, what is going to happen? 0 plus 1. I'll be getting 1.
1 plus n.
3 plus 4. How much?
1.
1 again. Okay, 1 plus 3.
4.
0 plus 4.
4.
Yes. So what set I got back? 1 plus n I got. You can check it. And that is why how we defined addition. Whenever you are adding a plus h to b plus h. What is the addition? A plus b
AB plus H. A plus B plus H.
plus h. That is what we are doing. So it forms a ring. Understood now? So instead of writing these many things, they have just uttered it. Here I am getting 1 plus n. Here it is 2 plus n. And last becomes 1 plus 2. means 0. So we get here 0 plus n. Followed? Then 2 plus n plus 0 plus n. What I'll get? 2 plus n. This becomes 2 plus n, 1 plus n, sum is 0 plus n. Then I add 2 plus n and 2 plus n. It gives me 1 plus n.
1 plus n.
This is so simple. So simple. The way I added, same way you can multiply also. What happens in case of multiplication? A multiplies to B, that's all. Sure? Followed my point?
Yes, ma'am.
Okay. Now let us be back here. So this was the definition of factoring. So I think you followed my definition. Okay, while giving definition, what they say, the R by N in the preceding corollary. So that is wrong wording. What you need to do is you start with let N be ideal of the ring R. The cosets, additive cosets of N form a ring R by N with the binary operations. This ring is called as factor ring. Okay. Now, fundamental homomorphism theorem. Fundamental homomorphism theorem. So now you are quite familiar with homomorphism, and now you are familiar with the cosets also. So I think now you have idea. See, what this theorem says, N be an ideal of a ring R. So R by N will be quotient ring. R itself is a ring, and you are defining a map gamma from R to R by N. How? If you operate gamma on X, it becomes coset X plus N. It becomes a coset X plus N. Then automatically it becomes a ring homomorphism with kernel N. So how would you go with this? How would you show that it is a homomorphism? So gamma of X plus Y. It will be certainly X plus Y plus N. But already you have defined the addition of cosets. So how would you add them? Can anybody help me? This will be surely X plus N, one coset, plus Y plus N. Do you agree? Addition of two cosets. This is our definition only. So gamma of X plus Y, what is it? It is simply gamma of X plus gamma of Y. So gamma preserves addition. Followed the point. Gamma preserves addition. Same way you can show that gamma preserves multiplication also. So they are showing how gamma preserves multiplication. They say additive part is done. So this way you can show. Additive part you can show this way. And what about multiplication? So gamma of X into Y, it is XY plus N. But we know the definition says this is just coset. And how the multiplication in cosets run? So it is X plus N multiplied by Y plus N, meaning there itself that it is gamma of X into gamma of Y. So gamma preserves multiplication also. Means gamma is a ring homomorphism. Followed the point. Okay. Okay. And now the next part, actually it's a proof they have not covered. Proof is not actually covered over here. But let us go to the statement, this being very fundamental theorem. Fundamental homomorphism theorem. What this theorem tells you? If suppose, let us see the picture also simultaneously. Phi from R to R dash is a ring homomorphism with kernel N. So R to R dash is a ring homomorphism. Now the R dash actually is a codomain. So image set will be something else. So phi of R is contained in R dash, as you know. So phi of R is a ring, and the map mu from R by N to phi of R. So this already you have defined. How you have defined this mu? Okay, mu of a coset is just image under phi of that particular X. Already we have done this. So this is an isomorphism. Now, if gamma from R to R by N is a homomorphism given by gamma of X going to X plus N, then for each X in R, this phi of X is nothing but mu gamma of X. So this is the very fundamental theorem. We are not going to prove it, but I think you got the meaning of what we said. So this is mu gamma of X. Gamma of X is going to produce X plus N, and mu operates on X plus N, giving back as phi of X. This is what we mean here. Okay. So what they want to say is phi is nothing but the composite map mu circle gamma. This is the actual meaning of fundamental homomorphism theorem. I repeat, phi is simply composite function mu circle gamma. This is the meaning. Is it okay? Okay, if not, I would like to go for you. Say mu of gamma of X. So what this will be mu as it is. And gamma of X is nothing but X plus N. Gamma of X is nothing but X plus N. Now mu operating on X plus N produces what? Phi of X. This is what the theorem says. Followed now? Okay, so just learn the statement. If it is asked anywhere, you should be ready with the statement. That's all. Keep all the labeled theorems ready for the exam. Okay, either the statements or the proofs, if they are given, be ready with the proofs. So I think up to this, you don't have any problem. So I would like to give this question to you as a homework. What you need to do is just find the addition and multiplication tables of 2z upon 8z. Can you prepare 2z upon 8z? Have to prepare 2z upon 8z. Just tell me, how will you go with this? What is 2z upon 8z? Is there any kind of division we are doing? No division is done. See, very first, what is 2z?
0 plus minus
0 plus minus 2 plus minus
Yes.
4.
Very good. So all multiples of 2, all integral multiples of 2. All right. What is the 8z then?
0 plus minus 8 plus minus 16.
So multiples of 8. Integral multiples of 8. So actually, let me list, as you stated, I would like to list it. 0 plus minus 8 plus minus, come on, 16 and so on. And if I take any member of this 2Z and multiply those elements, what is going to happen? All the elements will be back in the same set. So whatever you are doing after multiplication is a subset of this. So this particular is an ideal. 8Z is an ideal of 2Z. Now you are finding out 2Z upon 8Z means what kind of thing? So in 8Z, you're just adding members of 2Z. If you add 0, you get 0 plus 8Z. If you add 2 plus 8Z. Okay, you'll do so until all the elements are exhausted. All the elements are now back in your set. So that kind of thing you have to continue. So would you do it for me? I want you to write the set 2Z upon 8Z. After writing this set, I want you people to write the multiplication tables and addition tables. Can you? I hope you'll do it because less than 1 minute time is left. So I leave this to you. You have to write 2Z upon 8Z and just prepare addition table. Okay. So one of you is ready. It's a good thing for me. Anything else you want?
No, ma'am.
Okay. Thank you and good night.